Right, well, we're all glad that test is over with. I think you're going to like this unit a lot more than the last one, most of you. It's much more practical. There are lots of complicated looking formula here, but really they're just tools that you need to learn how to use. And except for a couple of strange situations, they're pretty straightforward. You just you have a problem to solve, you have an unknown, and you plug in what you know and you crank out the answer. Okay, so the first tool we're going to look at is called the law of cosines, and it's really just a more general statement of the Pythagorean theorem that you know and love. Right, Pythagoras' theorem, as we know, is c squared equals a squared plus b squared. But that only works for a right triangle, a triangle in which the angle C is 90 degrees. Okay, so the law of cosines, which is written here, c squared equals a squared plus b squared minus 2ab cosine c. Well, what would happen if that angle C, big C, was 90? What is the cosine of 90? Right, it's 0. So that minus 2ab cosine c, that would turn into 0 because the cosine c is 0, and we would just be left with c squared equals a squared plus b squared. Okay, so you can think of it as that this is where Pythagoras comes from. And this is a formula that we can use to find out things about all kinds of triangles, not just right triangles. Right, so here's an example. If we have a triangle where side A is 3, side B is 7, and side C is unknown, and we know angle C, 72 degrees, this is a perfect situation for this kind of, for this tool, the law of cosines. Okay, we're looking for side C, so we plug everything in that we know, and we solve, and we end up taking a square root. Make sure you're in degree mode when you do that cosine of 72, and we get 6.7. So try that and see if you can get the same thing that I did. Right, so that's not so bad. Now, underneath that example, you can see that I've written b squared equals a squared plus c squared minus 2ac cosine b. Okay, and then another one with a squared equals blah, blah, blah. So what I'm trying to say here is that the law of cosines is not prejudiced against any letter. You can use it in all three of those forms. The c squared equals, the b squared equals, or the a squared equals. As long as you get everything in the right order, it's going to work out. So this is definitely something to put on your next cheat sheet. Over here where it says SAS and SSS, what that means is side angle side and side side side. This is a good tool to use, the law of cosines, when you know two sides and the angle between them, or when you know three sides, okay, to find out the rest of the stuff about the triangle. So let's see how we can use it in a situation where we know all three sides. In that situation, you're going to be using it to find an angle. Right, so if I just take the very first version of the law of cosines that we used, the one from up at the top, that started with c squared equals, and we solve it for that cosine of angle C, then it'll look like it does here on the bottom left. Okay, and I've also done the same thing for the other two versions. So you can see how if we rearrange the law of cosines in that way, it's just about ready to be solved for an angle. And your book goes through several examples of both of these. One of the trickier examples is example 3. And really the only thing that's tricky about it is that you're not given distances, you're given speeds. And so what you need to remember is that distance equals speed times time. So in this example, one object is moving at 100 kilometers per hour for 2 hours. So that means it moves a distance of 200 kilometers. The other is moving 65 kilometers an hour for 2 hours, so it moves a distance of 130. But I think if you follow through those examples in the book, they will really help you to understand better how to apply this tool. If I'm wrong and you need extra help, let me know, and I'll go through some more examples with you in this way. Oh, what the heck, I'll go through example 4 with you as well. Okay, so in this example, the red thing is a tower, an antenna, that's being held down by 2 lengths of cable. The antenna is on a hill, which is why the whole thing is sloped up 12 degrees above the horizontal, and the cables that are holding it are labeled B and K, and we're looking to find out how much cable we need. Okay, we're told that 95 and 85 are the distances from B to C and from B to D, and we're told that the antenna, the red thing, is 100 high. Alright, and so what I've tried to do here is focus on angle CBA, and I've redrawn that down here, and I'm trying to show that it should be 90 degrees plus 12. Okay, CBA should be 90 and then 12 more. If you imagine that dashed line and then another one above it, parallel to it, the line CBD is a transversal, and therefore the two angles that are labeled 12 degrees there must be 12 degrees. I've done this in a different way than the book has, but in one of those ways I hope you can convince yourself that the value of that angle is in fact 102 degrees. Alright, so if that angle is 102 degrees and we know the side's 195, we can use the law of cosines to find the third side, which is B. And that turns out to be just over 151.5, I think it's feet. Okay, so now we have to find side K. Okay, from looking at the diagram, we can see that angle CBA plus angle ABD have to add up to 180, because that's a straight line there, CBD. So that helps us to find ABD. It must be 78. And we have another law of cosines triangle down here at the bottom with sides 185 and an angle between them of 78. So we can use the law of cosines as I've shown to solve for K, and it's 117. We add the two answers together to get the final answer for the length of cable needed, 268.59 feet. Okay, so that was a more applied, difficult example, but it's just using the law of cosines twice and adding the answers together. Here's an optional proof of the law of cosines. Skip it if you're not interested. If you'd like to know why it works, look at the red triangle up at the top. The coordinates of A is 0, 0. B is C, 0. That length, that horizontal length between the two is just C. And the coordinates of point C, we're just going to call X, Y. Okay? It's you have to move over X units and up Y units to get there. So now I'm going to take the left triangle out of that triangle that's just the left half of the triangle in red, and point out that the horizontal distance, the bottom of that triangle, the bottom leg is X, the length of it is X, and the leg on the right, the length of that is Y. And we can use that to show that the sine and the cosine of A are equal to Y over B and X over B. Rewriting, we find that X is B cosine A and Y is B sine A. Alright, so then we can ask the question, what is the distance of side A in the original triangle? And here's a reminder of the distance formula for the distance between any 2 points x1, y1, x2, y2. So if we apply that to the points xy, which is at the top of the triangle in red, and c, 0, which is point B at the bottom right, what we can do is we can find another expression for the distance that corresponds to the side length A. So doing that and using the substitution for x and y that I've already shown here, we find this crazy monstrous thing. Now if we underline those two parts in red and just rearrange them, we see that b squared is being multiplied by something, sine squared plus cosine squared, which is essentially 1. So that's how we simplify this thing to just be a squared equals b squared plus c squared minus 2bc cosine a. Okay, so it's not that magical. This is pretty straightforward proof. If you didn't follow it, don't worry about it. It was just kind of an extra for those of you that were curious about why this thing is true. Okay, enough talk. It's time for you guys to get some practice. For homework in this section, I'd like you to work on page 22, 1 to 37, every other odd. After you use this equation, this law of cosines once or twice, I think you'll see how practical and easy it is. Please, if you need more help, look through the examples at the beginning of the section. If that's not enough, let me know, and I'll send you guys some more examples.